Chapter 12 in-class exercise 1 problems. So these problems are based on position, velocity and acceleration calculations for rectilinear motion. Here we have been given velocity as a function of time and we need to calculate acceleration at t equal to 2 seconds. In the previous video we have seen that acceleration is derivative of velocity. So to solve this problem you take the time derivative of this function, which will be 4, and then that's constant, so acceleration at t equal to 2 seconds is 4 meter per second square. Second question, position is given as a function of time and we need to calculate velocity at t equal to 2 seconds. So to get the velocity we need to take the time derivative of position, and then it is 6t, and in that case you substitute t equal to 2 seconds, so it is 6 times 2 is 12 meter per second. That's the velocity. Now, for both of this problem, the solution is uploaded on Kodiak under Chapter 12 in-class exercises and solutions. So this is the solution of the first problem. Acceleration is 4, which is derivative of velocity. For second question, derivative of velocity is 60, and then t equal to 2 gives us 12 meters per second. Third problem is little bit tricky problem in the sense that the particle, we need to calculate the distance traveled by the particle as well as the displacement for the given time period. We have been given velocity as a function of time, which is 12t minus 3t square. So if you look at this function carefully, you will see that when time t is 0, then v is 12, which is positive number. When t increases, this term, negative term in the equation increases, which results in negative velocity. So what it means that particle is traveling from a point. Initially it travels towards right because the velocity is positive, and if we assume that going right is positive, and then at some point particle slows down because as t increases velocity decreases. You can see that from this equation, and then particle changes the direction and travels in the negative direction or towards the left. So the solution of this problem is given here. So particle is traveling, starting from here, particle goes towards right at first, and then it changes the direction and then it travels left. So for this problem, to get the displacement depends on the final difference between the final and initial position only. So first thing we need to do is we need to find the position function from the velocity function by integrating it, and that has been done here. So position is integrated. Now initial position data and time are given in the problem. So based on the initial condition, the position function has been calculated, which is given here. And now in that position function, t equal to 0 is substituted, which gives minus 21, because that you can see from the equation, and t equal to 10 gives us minus 901 meters. And displacement is the difference between this two only, which is final position minus initial position. That's minus 880 meters. The negative sign indicates that the particle has traveled towards left. Now for distance traveled, it depends on what is the total distance traveled from here towards right up to the point where particle's velocity becomes 0, and then all the way from that point to the back at t equal to 10 seconds. So for that we need to find out a point where the particles changes the direction. That is the point where its velocity is 0. And to find that point we need to substitute v equal to 0 in this equation and calculate the time. And at that time, when we do that, we get t equal to 2 seconds. So that's the point where the particle changes its direction. And this is our motion, like horizontal motion coordinate axis. So at t equal to 0, particle is at minus 21 meters. At t equal to 1, it's at minus 10 meters. At t equal to 2, it is at minus 5 meters. And at t equal to 10, it is at minus 900 meters. So the total distance traveled by particle from 0 to 10 seconds is distance traveled by particle from 0 to 2. So we need to find out how much distance particle has traveled from minus 21 to minus 5. Since distance traveled is always positive, we take the absolute value only, or the positive value. So it's 21 minus 5. And then what is the distance traveled by particle from 5 all the way up to minus 901? And that's given here, 901 minus 5. So the total distance travel is 912 meters. So take your time to go through the solution and try to and let me know if you have any questions. But this is like very straightforward problem. The only point to remember here is particle changes the direction. The problem that we will actually solve here, a step-by-step approach, is this problem. So let's work on this. Problem number 1213. Now, many of these problems are also in your homework. So so if you go through the in-class exercises and their solutions, that will also help you with your homeworks for Pearson Mastering Engineering. Now, you may have a different number in Pearson Mastering Engineering for the velocity or acceleration, but the approach is still the same. Tests reveal that a normal driver takes about 0.75 seconds before he or she can react to a situation to avoid a collision. It takes about 3 seconds for a driver having 0.1% alcohol in his system to do the same. If such drivers are traveling on a straight road at 30 miles per hour, which is 44 feet per second, and their cars can decelerate at 2 feet per second square, determine the shortest stopping distance d for each from the moment they see the pedestrian. So basically what we need to do here, that consider there are like two different drivers. One driver has no alcohol in his body, second driver has alcohol in his body. And they both are traveling in different cars at 44 feet per second. At the moment when driver sees pedestrian, it takes 7.75 seconds for a driver without an alcohol to actually apply brakes. And when the brakes are being applied, car decelerates, slows down, and eventually stops. So we need to calculate how long it takes for the car to stop from the point where driver sees the pedestrian. Okay, so from the point where the moment they see the pedestrian, that's the key point here. So let's put our like the coordinate system here. So we define the coordinate system. It's a rectilinear motion. So we define anything going right is positive. We have drawn this like horizontal line for rectilinear motion. This is the car, and this triangle indicates the pedestrian. So the moment driver sees pedestrian, that's our reference point. So this is our 0 point, or S0 is when driver sees pedestrian. And this is the point where brakes are being applied. Okay, so brakes applied. So this during this period, this is called like reaction time or reaction phase, where driver sees pedestrian but still brakes are not being applied. So car travels certain foot distance during that period, and this is the phase where actually car decelerates and then eventually stops before it reaches to pedestrian. So we need to calculate what is this distance s all the way relative to our reference point, which is S0. So let's call S0 equal to 0, where driver sees pedestrian, and relative to that point, we would like to define this distance. Car is traveling at 44 feet per second. That is the velocity of the car. So how much distance at this speed car travels during the reaction phase? So there are two different cases. So first we will talk about driver with no alcohol. So case number one, driver without alcohol consumption. So for that, the distance traveled during reaction phase. So S reaction is equal to simply the so velocity is equal to distance divided by time. So distance is equal to velocity multiplied by time is equal to simply speed multiplied by t reaction time. So speed here is 44 feet per second and time is 0.75 seconds. So that gives us 33 feet. Now, so before even driver applies brake, car actually travels 33 feet and then car decelerates. Now, once the brakes are applied, then acceleration of the car, deceleration of the car, AC, is constant, and it is given in the problem as 2 feet per second square. So since it is deceleration, we substitute negative value for that. So remember, acceleration is when speed increases with time, that is acceleration, and that is positive. When speed decreases with time, it's deceleration, and that is negative. And since it is constant, we can use one of the three pre-integrated equations that we have seen in the during the theory portion. So we can use one of these equations, v equal to v0 or s equal to s0 or v square equal to v0 square, depending on the problem situation. Now, what we do not know about the problem is how long it takes for the car to stop. So we do not have any information about time t. So we do not want to use equations 4 and 5 because both these equations require time t. So we can use third equation or the equation number 6, which is v square equal to v0 square plus 2ac s minus s0. So let's write down that equation here. So v square equal to v0 square plus 2ac s minus s0, where v is the final velocity of the car when it stops. So obviously when it stops, its speed is 0. v0 is the initial speed of the car when brakes are applied, which is 44 given in the problem. AC is the minus 2. So it's like 2 is the part of equation and AC itself is minus 2. That's given here. So car decelerates. S is the final position and initial position is our reference point, which is 0. So when we solve this equation, we get S equal to 517 feet. That means from the moment driver sees pedestrian, car travels 517 feet before it stops. So this is where car stops. Now, this is for person without alcohol in his body. What we need to do next is we need to exactly do the same thing, but for person with alcohol in his body. So what changes between these two cases is the distance traveled during reaction phase. So for driver with alcohol in the body. So for that, S reaction time will be again speed divided by speed multiplied by T reaction time, and speed here is 44 and reaction time is 3 seconds. So that brings us to 132 feet distance traveled before brakes are being applied. And then the remaining portion is still the same. So AC, once brakes are applied, the car doesn't care like whether the driver is alcohol, without alcohol. So car will mechanically it will stop with the same rate of 2 feet per second square. So we apply this equation to AC s minus s0, and final velocity is 0, initial is still 44, this is 2 minus 2 s minus s0. There is okay, so one thing we actually should have counted here is that, sorry, this s we define S0, we define this point as our S0 when brakes are applied. So our reference point is here. This is the and relative to that we measure this distance S0. So sorry, my bad. So we need to substitute S0 equal to 33 feet because that's the distance traveled by car during the reaction phase. So you substitute that here and then get the total distance 517. Same for the second case, we substitute S0 equal to 132 feet in this equation and then solve for final S. the distance traveled by car, we get 616 feet. So you can see almost 100 feet more distance traveled by car when person has alcohol in his or her body. So once again, I would like to remind you that S0 is, we don't define this position as S0. That's just our reference point or origin of the coordinate system. S0 or initial position when brakes are being applied is the position of the car at the end of the reaction phase. So that distance is different for both, like driver with alcohol and without alcohol, and that changes the final answer. And now we work on the last problem from that this in class exercise. Is a ball is being thrown vertically upward with a speed of 15 meters per second. Determine the time of flight when it returns to its original position. So let's draw a diagram. So this is our position, like initial position or reference point. As well as for this problem, we assume that this is our initial position. When a ball is being thrown upward with 15 meters per second speed. Now ball goes up, and because of the gravity, the speed of the ball like decreases as it goes up, and then at some point it becomes zero, so it no longer goes travel upward, but now because of gravity it comes down and it comes back to the same point. And what we need to do is we need to calculate this time of flight, how long it takes for the ball to come back to the same position after it is being released at 15 meters per second. Now during this motion of the ball, the ball experiences gravitational acceleration, and the value of gravitational acceleration g is 9.81 meters per second square for SI system. For this problem, because the initial velocity is going up, we define our coordinate system as positive going up. So gravitational acceleration is acting downward, so we need to consider that as negative, minus 9.81 meters per second square. And since this value is constant near the surface of the earth, this is the problem of constant acceleration. So once again, we can use one of the appropriate equations here. So since we are calculating time, we need to use either equation number 4 or equation number 5. Now equation number 5 makes more sense because we have some information about the initial and final position of the ball, and they both are same. So S is equal to S0 in our case, so we can use this equation and calculate time of flight. We also know the initial velocity of the ball, and we also know the gravitational acceleration. So let's go back to this problem and write down this equation. S equal to S0 plus V0t plus 1/2 ACT square. Now S and S0, they both are same for this problem, so we can put them, like we can put 0 here because S and S0 are same, equal to now V0t plus 1/2 ACT square. Initial velocity of the ball given as like 15 times t plus 1/2 minus 9.81 t square. So when there is only one unknown in this equation, and that is time, and once we solve for that we get 3.06 seconds. So this is the time of flight. So ball takes 3.06 seconds to go all the way to top and come back to the same point. Thank you.